All right, so here's the rest of number 95. I did the first part of it in class, but then ran out of time. So the full premise is I got this car headed towards this barrier. There's a certain distance the barrier is in front of the car. The car's driving at a certain speed, given textbook value. And then it takes a certain amount of time. There's a time delay before the driver notices that the wall's there, right? So maybe a certain reaction time to switch his foot over from the gas to the brake, right? Now, we had to do this, convert the speed into meters per second, so we could apply these equations. And this was in two parts, right? Two parts to solve part of it. First, you have to figure out what is the distance the car went while the driver was going through this reaction time, this delay. So the speed of the car was going constant for a while for the reaction time. Now, my numbers, I got half a second, right? Took about 13 or 14 meters of road. Car got to about here before the guy finally started slamming on the brake. Then he does slam on the brake. He brakes at this rate. Here's the acceleration. It's a negative acceleration because he's braking to stop. Okay. How far did he go? Pull up the third kinematic equation, plug in initial value of this. Right. Now, the final value I set to 0, the idea being that let's take away the barrier and see where would this guy naturally come to a stop at this particular acceleration, at this particular initial velocity. You can solve that, and it comes out to an additional about 42 or 43 meters. So the question, does this guy slam into the barrier? Well, if you add up these two parts, right? So here's the distance he was going while he was switching his foot over from the gas to the brake, and here's the distance that he was slowing down over. 13 plus 42 adds up to more than the original 50 meters. That means this guy's out of luck. Yeah, he's gonna slam into that barrier, but maybe not very fast. Might be going kind of slow. And the reason is because 13 plus 42 adds up to just a little bit more than 50. It's like, if you only had about 6 or 7 more meters of road to go, you would have been good to go, right? Now, here's the part I did get to in class is, what if you rearrange this question? What if you said, what would the maximum speed be, the maximum original driving speed, so that he avoids hitting it? And by avoiding hitting it, I mean, let's say that he skips to stop, just so that the front tag just barely touches that barrier. Right? So it just takes up this full 50 meters. What would that be? See, before what the 50 meters was good for was just comparing. So his natural stopping distance would have been a little bit more than 50 meters. So it's like, it's more than 50 meters, he's out of luck. Now let's set this as like a hard value. Like, okay, he's going to go to 50 meters. How fast could he have been driving at a maximum? Right? So the way you can solve this is with a system of equations. I know that there was a certain time delay while he was traveling at a constant speed. Constant speed times time gives you the amount of road that he would have covered going at that constant speed. Right? Then when he hit the brake, he would have taken up more distance. Right? And we used the same equations before. I'm just spelling them out again. Right? And the key here, here's where the third one's going to come in. This is for the new context, that these two distances, the distance that he was switching his foot over, the delay distance, and also the full braking distance, they have to add up to exactly 50 meters or less. Maybe I should make this an inequality. It can be this at a maximum, right? So see if you're trying to hit a maximum value, right? Maximum initial speed to do that, right? Now, if you plug in the known values, I know his reaction time is, say, half a second. The final velocity would be 0 if it comes to a full stop. Again, it'd be full stop right at the barrier, just like right there. That's what that is. And then this is the rate that he could slow down, 9 meters per second squared. It's negative because he's braking, right? And I also want the two two distances, right? The delay distance and the brake distance to add up to exactly 50 meters. Right? Got a system of equations, 3 equations and 3 unknowns. Right? At this point, the physics is done. Like if you got to this point, then you understand the physics. Right? The rest of this is just, can you solve a system of equations? Right? And you might see that there's going to be a quadratic equation that comes out of this. So the way I went about this, right, might do this a little bit different. I took this second equation and rearranged it to solve for x. To solve for x brake. Right. So subtract the v naught squared over, divide by the 2 times acceleration. Right. So there you go. Set that up. Good. Now, why would you want to do that? How would that be helpful? Right. Because remember that adding the delay distance and the brake distance together has to add up to exactly 50 meters. Right? You can rearrange. We've already got x delay. Right? It's equal to this expression. So I've got this expression plus x brake. So just rearrange the second expression, which is what I did right here. Right? You add these two together, and they have to add up to exactly 50 meters. Right? So if you do that, you got this expression. That's right there. plus this expression right there is equal to 50 meters. I did throw in one more algebra step, which is subtract the 50 over and set it equals 0. Now, the specific reason I did that is because look what we're solving for. We're solving for V naught. It's being squared here, it's not squared here, there's an extra constant. I set it to 0 because now it is in a form where I can apply the quadratic formula. Exactly right here, made a quadratic equation. Run the quadratic equation, V naught equals negative B plus or minus the square root of B squared minus 4 times A times C, where A is 1/18 and C is negative 50. Right? Keep all your signs up. All divided by 2A, which is, it comes out to 25.8 meters per second with the numbers that they gave you. Now, last thing you'd want to do is go back and check and make sure that that actually makes sense. Remember how the first part of the problem, they just gave us the original speed and they said, well, where would you come to stop? Is it before or after 50 meters? And it came out to just a little bit more than 50 meters. Was that like 56 point something, I think, right, meters? Which is, he just barely ran out of road. So, this 27 meters per second is a little too fast. If only it was a little bit slower, then you probably would have been okay. 25.8 meters per second. Yep, that's just a little bit slower. So that checks out. It makes sense. And we are good.